Hello? I don't know if anyone can hear me. Who knows? I have no idea if the audio is working. So I'll just wait a moment and see in the chat because I've never actually streamed with YouTube or any of this before. So it's probably going to go horribly wrong. No sound at the moment. Bum. How do you sound? Ah, you can hear me. Okay, I think I'm just going to get started. I don't really know what I'm doing. I'm not going to cover anything about dreams or media molecule stuff on this stream. It's going to be a super geeky electronics stream. I'm a noob at electronics, and I've only recently started getting into this hobby as a way to like chill out after making dreams at the end of the day. And I found it really rewarding to basically be able to make things that are physical. And I think it's a magical time to be doing electronics. If you're not into eurorack, my plan today is basically to just go through the sort of recipe that I've ended up falling back on, because there's actually only so many building blocks that you can get in a there's only so many building blocks that go together to make a eurorack module. So if you don't know what eurorack is, you're probably going to be quite lost in this. I'm going to go quite fast into electronics and PCB design and stuff like that. We'll see. I'm not really sure. I haven't planned. So this is a module. These are some components. In fact, let's start with a classic module not made by me. So this is the Verb. It's a eurorack module, which is like 5 inches high. I'm putting it sideways here so it fits in camera. 5 inches high, and then you can have them as wide as you want. And basically, they've got some jacks which take voltages, either audio or control voltage. And I said I wouldn't do dreams, but you can think of them as like literally like wires. And then you've just got knobs. And that's about it. The building blocks of eurorack are incredibly simple. I actually hate it as a format. It's awful. But it's also extremely simple and universal, which is why it's so successful. And the back of these things, you typically have a power connector. So that's a little power connector. And you plug it in with one of these horrible little cables. And the funny thing is, especially with these digital modules, there's only so many ways you can wire them up. I'm just going to have another look at the chat. I'm not actually keeping an eye on the chat too much. But bit of corona cough there. I hope not. I hope everyone's safe, by the way. But anyway, so yeah, if the stream breaks or something, shout on the chat, and every now and then I'll jump across to the chat window. Otherwise, I'm just going to waffle to myself for hours. I wonder if I can record at the same time. Who knows? Okay, so this is a classic eurorack module. I thought it might be fun to actually take this one to bits. I've never actually done that. So if I just, this is quite a classic construction. You have a front panel made of aluminium, then you have like an analog board that's doing all of the sort of op-amps and things to get things to the quite high levels that eurorack likes. And then you'll typically have a digital board, and I'm going to assume that that's the case here. And I've taken the screw out that's holding the backboard on. I didn't think this camera through very well. Maybe I'll do it on another camera. Let's see. Let's try this camera. Okay, this is harder than it looks. Respect for YouTubers. So there's the module. And if I just pull, as I said, I've not done this before, so quite intrigued as to what's inside. Oh, it's not coming. So the other thing about eurorack is it's quite an expensive hobby. These modules sell for a few $100s at least, especially the digital ones. And the thing that I think is amazing is that you can make these things for about the same price that you can buy them. And I find it much more rewarding to make my own and design my own. Okay, so we've ripped a several £100 reverb module into 2 pieces. And this is the digital board. I'm looking at it for the first time. What have we got? Let's put it back under the other camera. Not my desktop. There we go. So that looks like we've got a big, oh look, it's an STM chip. I think that's probably down to Eric Brombaugh on Twitter has been helping me out, and I believe he actually he's been doing this for years. He did an STM board. STM is ST is a French company that makes this line of processors. And what I wanted to talk about today was that basically, for no particular reason, ST seems to have a long lineage in Eurorack. And I stumbled onto it after playing with Teensy. It just appeals to me. It's got some nice things. The chips are indestructible. They come in a variety of sizes and flavors. So all you've got in a typical digital module is an STM chip. This is one of the bigger ones with lots of pins. It looks like it's you can probably read it better than me, STM32F427. So that's a ARM Cortex M4. So it's, Pentium sort of level power. And you've got a memory chip here. So this is a reverb, so it needs a fair amount of memory. This is a classic codec, one everyone uses, which is a Wolfson Micro, Scottish, Edinburgh-based thing that got bought out a few years ago. That does your stereo. So this converts the digital signal from here into the audio. We'll talk about that in a minute. Little crystal and some power regulation. I think one thing about Eurorack that I hate is that it's 12 volt, plus minus 12 volts. Let's look at the chat actually. So basically what comes in on this little power cable is plus 12 volts ground and minus 12 volts. So if you want to run 3.3 volts here, you have to run it through a regulator. And most Eurorack modules don't go with a switching regulator, they just go with a linear regulator, such as this puppy here, which will be dropping 12 volts down to 3.3 and just spending the remaining, whatever it is, 8.7 volts as heat, which is horrible. So I tend to design all my modules using the slightly less common but wider 16-pin thing, which basically adds nothing very useful apart from a 5-volt line. And at least then you're only dropping from 5 down to 3.3 and boiling fewer oceans. So I feel like it's my ethical obligation to use the wider pin count thing. So there you go, that's a digital module of an Adverb. And as a reminder, it bolts onto the back of this, which will be a much simpler analog board with a bunch of op-amps. So that's the classic construction. And just to quickly cover off some other modules, this is a Music Thing modular startup. This is actually the prototype that Tom kindly sent me before he knew who I was. I managed to wangle one via filling in a nice Google form. This is a very simple module. There's no processor here. This is just well, maybe there is actually a tiny processor, but this one basically is a headphone mixer and a little trigger output. It does rhythms and some clock output. And this is the construction that I'm actually going to talk about mostly today, where basically you have a front panel. You wedge some of those little components that I have over here in between the two layers, and then you put all the electronics on the back. And so if we look at this closely, it probably amounts to a few op-amps, the power connector that everyone has. This will be an op-amp, probably a small processor somewhere. I don't know, that's probably a headphone amp. One of these will be a little processor, and that's about it. So that's startup. And you can take that kind of two-layer style much further. So this is a Mutable Instruments rings, again, which I haven't ripped apart before. So let's brutally take this several £100 boutique piece of audio hardware to bits, because that's fun. Oh, they're quite stiff, these. Right, I've taken off all of the jacks of the sort of, I don't know what you call them, bits that hold it together off already. Yeah, chat's quiet, so I'm assuming you can all still hear me. So this is that same two-layer effect. You've got a nice aluminium board on the front, pull hard, and a ha-ha. So here, Emily, a Parisian famous module designer, has packed everything onto a single board, the analog and the digital. In the middle there, it is, yes, once again, an STM. What's she put on here? STM, I bet you it's an F4 or something. I can't read it, but it's probably an F4. Exactly the same codec that the Adverb used. This little W, my finger doesn't do backwards. Let's just look. This little chip here is a codec that's doing the audio. It's like a sound card in the chip. And then the others will all be op-amps to drive these jacks. So yeah, that's it. I mean, all a Eurorack is, what am I trying to say? Eurorack is enormously fun to play with his music, but if you're building these digital modules, the joy is the thing that makes a Eurorack module interesting, I think, is the physical design or the particular idea you've got, right? The building blocks are not interesting. And I kind of wanted to show on the stream how uninteresting the building blocks are and how easy they are put together, which means you can kind of, I find it brainless. It's not like we're doing kind of cutting edge FPGA or electronics sort of thing. It's the opposite. It's like super easy electronics, building block Lego stuff. And therefore it's really rewarding because you don't have to think too much and you can actually apply your creativity in the same way that, all game programmers have the same C, we all use the same building blocks. But it's how you put the building blocks together that makes wonderful modules. And Mutable deserves a huge shout out because basically Emily put all of her designs as open source. So although you can buy the module physically manufactured in France, I believe, you can actually download all of the PDFs, which we'll do in a moment. Okay, so that's sort of classic modules. I've been working on Plinky, which you probably know if you follow me on Twitter. This is the expensive version. If I do the rip it apart thing, it's the same construction. This is a giant STM again. That's a little, I use a different codec. It's a weenie codec. Can't remember who makes that codec, and I actually have two of them on this because it's a ridiculous. This is the ridiculously expensive edition of Plinky, because the front panel isn't made of aluminium. The front panel is itself got another STM. I mean, I think as I said on here, it's not in focus. Basically, if at first you don't succeed, add another processor. So basically, I couldn't make this front panel work, so I just added a whole other STM processor. And then it communicates with the front through this. Massive overkill, ridiculous. But I kind of like the physical form factor. Go and look at chat again. Is everyone enjoying it? Okay, what are they saying? Blah, blah, blah. Blah, blah, blah. Yes, it seems. Yes, I'll open source everything I do. I owe it to Emily and all the other people who've contributed. And I'm going to design a module on the stream. Yes, in theory, not a complete one. I'll skip a few steps, but we'll do all the steps in Accelerate 2. This is Plinky Cheap. So basically, I had rage, so I put everything onto a single. This is Eurorack sized, so you can see it has mounting holes, but it's only a front panel. Hilariously, it does mean it's a bit ugly because the jacks and the screen have to be mounted on the front. These are actually encoders, as in they're clicky round things that go on forever. They have to be mounted on the front, and then I actually have a battery connector for a rechargeable battery and a USB port, and then headphone jacks. So the idea is that you can use this completely standalone without Eurorack, and then power it from USB or a battery. And then it's super cheap because it's just a single. This probably costs about $20. And then the idea was that there'd be a second board that would mate underneath and then provide Eurorack things. I may still do that. I don't know. That's work in progress. And last of this intro section, this is BBO, which is a little module that I designed after a weekend random thought, which is following that classic two-layer design. So this is quite dense. It's got a USB port for plugging a keyboard in, because you can actually type onto a little computer. Got a bunch of knobs. And yes, once again, the STM. So as you can see, the building blocks are the same again. You've got chip, a couple of op-amps, power. I've got hiccups, excuse me, and I can't remember what that is. It's probably another op-amp. So that's BBO, which is basically a programmable oscillator. So you type in code, and then it compiles it and then evaluates it in order to create a waveform. So that's going to be fun. And this is a cheap way of building front panels. There's a website called Schaefer, and they're German. They have an American subsidiary, which I've forgotten the name of. But if you go to Schaefer panels or something, they will make these incredible aluminium panels for you, but they're a bit pricey. But basically, it's amazing. You download a CAD program, you draw in where you want the holes, and they send you some aluminium stuff, and they normally throw in a Haribo into the box, which I think is very nice. This is a PCB. So part of what I'm going to talk about later is the magic of the PCB houses, because basically the Chinese PCB houses are just incredibly cheap, but also the service is incredible. And the thing I wanted to talk about today was the assembly service. So this is a BBO that I've soldered all of the sort of hardware to, if you like, the knobs and the buttons, the clicky buttons, and the sort of screen is off eBay for £2. But you can hand solder all this stuff, and for the first 9 months of my hobby, I was basically getting bare boards back. So you'd get a board. Let me show you what a bare board looks like. This is a bare board for Plinky, the front panel. And so this is just what you get manufactured. This probably costs, $20 for 5. I don't know. Can't remember. Not very much. This was made by All PCB. PCBway is another one I've used, and JLC PCB. They're all pretty much a muchness as when it comes to PCB. I think they actually use the same factories and outsource them. I don't know that, but they're indistinguishable from each other pretty much, and they're all incredibly cheap and good value. So this is a bare PCB, and basically what you have to do is then you have to solder all of your tiny bits on, and these are 0.5 millimeter between the pins, so it's quite fiddly. And you can do it with stencils and baking ovens and stuff, but I didn't actually enjoy that very much. I mean, it was cool, but it would take me a week, and I didn't do it very well, and it was very frustrating. So I always thought assembly was out of reach. Actually, this was professionally assembled by All PCB. I did 3 of these by hand, and it took me a few days to do each one. You have to basically hand solder, 144 pins, 0.5 millimeter apart, and then all of this stuff. And it's not actually that hard, but I'm not good at it. And this would take me, after I get home from work and hang out with a girlfriend, put the kids to bed, and then until about 2 a.m. in the morning, I'd be working on this. Probably take me 3 or 4 hours to build this board. And often it didn't work. Kids' artwork on the back. But that was expensive. This cost me like $200 to get that assembled and made, and that's not cheap. But JLC do this incredible service. I don't know what they've done, but they've optimized it in some ways. I'm going to talk about constraints, creative constraints later. Basically, they will do assembly for you in runs of 2 or 3 or 5 for almost no money, like $7 plus the price of the parts, which is ridiculous. I mean, this was a few bucks to get a simple board, and it worked first time. I was just so impressed, and it's changed everything for me. So that's what I want to actually work through today, is like, how do you go from an idea through to getting one of these in your hands? And there are lots of tutorials online, so I'm not going to do the sort of blow by blow. I'm going to do sort of the tips that I've learned along the way that can get you from here to there. And on another stream, I'll do the bring up and the software side. But for now, I'm just going to talk about hardware. All right, that's enough of waving eurorack modules at a camera. Let's start building something. I'm just going to have a look at chat for a second. Wish more modules had standalone options with eurorack cases being stupid expensive. I agree. And I really like the idea that, the pocket operator style. So LPZW modules on Twitter, huge shout out to him, Leipzig West modules. He's been all the way through my journey. I DM him like, oh God, tell me about resistors. Not quite, but he's been really helpful, along with Eric Brombaugh. And he made a pocket operator where eurorack adapter, where you basically take your pocket operator, which is a little standalone synth, and you can kind of bolt it into eurorack. So that's where I got the idea for this Plinky that's standalone, which I just love playing. Like, Plinky is just really fun to just play as a little instrument. But then the idea was that you can modulate it and control it and use it to control eurorack. I'm not quite there yet, but I'm pretty happy with that. Crossover. Right. So I was talking about STM and why is it so widely used in all these modules. I think partly it's that Emily from Mutable has been using it, and Eric have open sourced their design. So the other reason is because this is sold on Amazon by ST. It's a Nucleo development board, and all it is a ST chip, an STM chip. You can get them for all of their chips, so there's a bewildering array. Basically, here's we go into the numbers. So you've got STM, then you've got a family, which is like F or H or L. L is low power, F is fast, H is hyper fast, I guess. It's a new one. And then you have a number, which is sort of how beefy it is. So 0 is like a Cortex M0, so it doesn't have a floating point. You can use it to do little, control voltage type stuff, maybe. Then you've got the 4 range, the 2, it goes 2, 3, 4, but skip straight to 4. Everyone seems to use the 4 for audio stuff, so like reverbs and delays. And then you've got the 7. So expensive Plinky uses a 7. H7 no less. So this big chip here is running at like several hundred megahertz. It has caches and it's super fast and it's just juicy. Lots of MIPS. Whereas most of the other modules I've shown you are basically F4s. This is an F4 here, I think, or possibly an L4. I don't know. Point is, the crazy thing is they sell these at a loss. So this is £10, I think. And you can get this, plug it in, and have a blinking light in 1 minute. And I think that the fact that STs sell development boards for so cheap, and then you plug wires in to connect to the pins. So literally every single pin on this chip is available on these headers here, all 64. And you've got a button and a light and a couple of things. So it's a bit like a TNC development board, but there's a much more obvious path to your own PCB. So I think that's phenomenal. I should have planned this stream really. And yeah, I'm sorry if this is badly pitched or, I'm about to dive in even deeper. But I hope you enjoy it. And so what makes up a eurorack module is, there's a little display, runs over ITC. You've got knobs, buttons, LEDs. The module that I'm going to show you a bit of today, I found these in my drawers. It's an 8x8 old school grid of LEDs. You feed positive into one leg, which is the rows, and negative into the other leg, which is columns. Depending on which one you feed in, that LED lights up. I was like, okay, 16 pins, connect them to the processor, job done. And basically, all this is doing is connecting STM processor in the middle, so a few input jacks, a few output jacks, and that's it. I think nothing more to it. Let's do it. So here's kicad, free open source thing. File, new project. Let's do it, man. New project. What should we call it? This is completely unrehearsed. I shouldn't have done this. In my Dropbox. Let's call it stream. Right. So the first thing you do is open up the Schematic Editor on the wrong. Yeah, there we go. And you just start drawing. Oh no, I'm going to do this in a different order. So you have to have an idea in mind. I'm skipping that part here because I want to show the building blocks, but I do think it's helpful to actually have like a creative idea of a module that you actually want to build. And basically the idea of the Schematic Editor is that you just you press A and it takes forever to load up my library of stuff, which is just a standard KiCad library. People spend ages building their own stuff, but let's see if they have any STMs. Oh, they do. Let's go for a 405. I'll explain why I chose that one in a moment. So this is the 64 pins. Annoyingly, the ones in kicad, they don't do the pins in order. So basically you have 1, 19, 32. They've grouped them logically rather than physically, if you like. So the pins that you see here aren't the same order as the pins on the chip. And that's it. And now we literally just connect things together. So let's say that we wanted a jack input to take audio, not audio, and let's take a control voltage in. Now we're going to need an op-amp because basically, and this is something I learned that you can steal from Mutable Instruments. The MCP 6004, that's 4 op-amps. You have a 602, which is 2 op-amps, 601, which is 1 op-amp. It's a really handy chip. So basically, it's made out of 4 op-amps. Let's put them all down. 1, 2, another one. So if you notice, these have different pins on them. 4, and then the power. Come on. There we go. Okay, so we've got, by putting down those 5 pieces, I've basically got all of the thing, and automatically I'm just going to throw a capacitor across the power supply. I'm going to set it to 100 nanofarads, and I'm going to wire it I'm not going to teach you how to use KiCad. I'm just going to show you how I use KiCad. So all the real electronics people are probably going, oh my God, what a mess. This is horrifying. And in a minute, I'm going to load up one of these I made earlier, sort of Blue Peter style. Let's have a 3 volt 3 rail, wire it on. And they'll just say, oh my God, the mess, Alex, what are you doing? But my point is, we're not saving the world. We're not making ventilators, unfortunately. We are just making entertaining gadgets to have a creative outlet. And so, don't overthink it. I can sketch one of these things out in a few minutes and get pleasure from that, and then it can be manufactured and made in my hands. I think that's just incredible. Quick look on the chat. This brings up memory for Heil. Yeah, I'm not sure how anyone should yell at me if I write in all caps and go, "You're all evil" or something. I don't know. Anyway, back to the training. So yes, I've got my what am I doing? Sorry, I'm new to the streaming thing, so forgive me. Let's wire up a single let's wire up a single op-amp to illustrate an input. Oh, come on, Gavin. Why is it still in? Some of my shortcuts are not quite working. Okay, so M is move and X is flip, because I always put minus on the top. So watch out. I've actually manufactured things where I got the minus and plus the wrong way around. So the classic way to do this is let's stick an audio jack in. So we want a audio jack with a now Thonk. Shout out to Thonk in Brighton, amazing DIY hobbyist shop. I think we want the switch T. Yeah, there you go. So basically, they sell these little jacks. I can show you one. Well, they're basically all the jacks. Here they are. These little bad boys. They're universal on basically every eurorack module ever, and they've got 3 pins: shield, tip, and tip normal. Basically, when you don't have something plugged in, tip normal is connected to tip, and when you do, tip normal becomes disconnected. So the classic thing to do is, the other thing I'd recommend, top tip, is the most useful command in the schematic editor is C for copy. Basically, once you have something like a ground or a resistor or a capacitor, just copy it. Don't go back to your library, just use C to copy it. It's so useful. So I'm going to ground the normal, so that means that when nothing's plugged in, the tip is connected to ground. And I'm also going to messily just hook my shield into ground. So that's the ground of the lead. It's basically what you want. And we're going to hook this in an inverting op-amp. So let's stick a resistor in. We haven't got any resistors yet. So there's a resistor. It's getting a bit cramped. Let's move this over. So yeah, everyone knows a inverting op-amp, of course. You just shove that in. Capacitor, a resistor across the inverting feedback. And we want to low pass this bad boy so that we don't have any horrible ringing, and also because we're going to be sampling this digitally. So for a CV input, you might choose, well, I'll get to that in a minute. Oh, we better ground the other one. There we go, job done. Messy as hell, but there's my inverting input. And then I normally just label that as, we'll give this a name. So maybe we've got an idea that this input is going to be the gate or something like that. So it was a gate. Give it a gate. And now we can hook that to one of the analog pins. I need to talk about how you find out which pin to use, but we'll get there in a minute. Wire that up. Right, so now that's basically saying someone plugs a jack in there, it gets fed through. Now, the input impedance of eurorack should be 100K, basically. 10K minimum, 100K typical. So this point is grounded, right? Because it's a virtual ground, because that's how op-amps work. So this pin's grounded, therefore that pin's grounded virtually. So we've got 100K to ground. So basically, whoever's plugging a jack in, they're having to drive a 100K load, which is, the right balance of noisy. If you go too high, it's too noisy. If you go too low, too much juice demanding of the guy who's sending or the girl who's sending. So 100K is about right. That means that we now can choose our gain. So let's say we wanted this input to be like plus minus 5 volts. That's a 10 volt swing. And this little puppy is definitely not going to be able to take 10 volts. It'll go bang. So we want to scale it down to 3 volts, so 10 down to 3, about a third. So let's give this one 33K. And then we can choose the amount of filtering we want. So basically it's 1 over 2 pi RC, I don't know, 220 picofarads. I'd probably get a piece of paper out and figure out what the actual cutoff frequency was by just basically multiplying that by that and doing 1 over 2 pi RC. But yeah, that'll do. So yeah, we've now got a little input circuit connected to PA10. Now, I just want to point out how simple SCMs are. Basically, all of these pins across the top, you hook them to 3 volts. This reset pin, I'll show you later, but basically if you pull it down, it resets the chip. This pin, if you pull it high, it blanks the chip out. So that's your panic pin. VCAP is just, they can't build capacitors on chips, so you have to hook a couple of capacitors to it. So you literally kind of go capacitor, and then ground. Job done. Yeah, like that. and the other one as well. God, I suck at drawing. Come on. Why is it not drawing a wire? Everyone who knows kicad better than me is like, what the hell's going on? Oh, I've messed that up completely. Wire. There we go. Wire. There. Wire. There. And yeah. Check over on the stream. Oh my God, Demes, what are you doing? Yeah, indeed. So yeah, I've got capacitors down there. This will be a clock. Shove a crystal across it. You don't actually have to. The hilarious thing about SCM is they have an internal clock, so you don't have to bother putting a crystal across here. But if you actually want any accurate timing, shove a crystal across there. These are all general, so you can do what you want with them. Shove these to ground because they're the grounds. More general pins for your LEDs and your displays and your gates and your knobs. And if you want to know how easy it is to do a knob, holy moly! This is my point is there's very few patterns. There's input jacks, scale it to the right level, shove it into the chip. Then you'll have pretty much the same thing on the output, but scaling it back up again for an output jack. And then you'll have a couple of switches, job done. It really is that simple. So you can draw this stuff in a matter of minutes, and there's not many patterns that you see. So if I in fact, let me just prove that I'm not just lying. Blue Peter style. Here is Clouds, a very famous module. Just double check that OBS hasn't crashed or anything. Nope. So this is Clouds, and as I said, Musical Instruments put all of their modules up for free. Here's how you do a knob: ground, power, pot, the end. Ground, power, pot, and these labels are just connected to his SCM somewhere. There you go, pot, pot, pot. So incredibly easy, and he's here. His control voltages, texture, size, position. They're just coming from. That's audio in. Here you go, position, density, size, volts per octave. That's a pitch, blend, texture. So he's literally done exactly the circuit I just built. If we go and look in kicad, basically jack, resistor, feedback resistor, capacitor. There you go. Aha. So I forgot to say, this is minus 5 to plus 5, and that gives you a swing of, we've scaled it to be about a third. So, plus minus 1.6 volts here, which is fine, but we don't want negative voltages because we're in digital land and when the ADC expects 0 to 3, so we have to bias it. And the easiest way to bias it is actually just to grab one of these puppies and shove a negative voltage in. So we just go, right, I want a negative voltage. And so you just say, label it and say, let's say minus 5 volts. And I think Mutable tends to use 10 volts and then double the resistance here, which is exactly equivalent. And where do you get 5 volts from? Well, you get it from a Zener diode. So easy peasy, just LM4040, 5 volts, right? And you just reverse bias it. So you want to basically have, let's have a resistor here, little voltage divider, shove some current in the top, and we'll use our fact that we're on eurorack, so we've got minus 12 volts kicking around thanks to the magic of eurorack power supply. So we've got 12 volts here, we've got 5 volts here, so we've got 7 volts here. So if we do 7K, we'll get a milliamp flowing through there, and tap it off with a wobbly line because I'm on the stream. And I'm using a touchpad here. It's horrifying. And we'll call that one, what did I call it? Minus 5 volts. There we go. So I've made my, let's stabilize it a bit with the capacitor because we're good citizens. I don't know much about electronics, but basically they're like, stick a capacitor across it if you need to smooth it out a bit. Job done. Right, there's our minus 5 volt reference. So basically we're using this as a sort of summing amplifier, and we're basically saying minus 5 volts. So when you put plus 5 volts in here, this minus 5 volts cancels out, you get 0. So you get 0 out. When you have plus 5 volts and minus 5 volts here, you get 10, other way around, sorry. When you get minus 5 and minus 5, you get minus 10, which is then inverted to a third and it's inverting, so you get 3 volts. So basically, you get the answer. Now, why do I sound so confident? Because I'm sort of sharing the result of fiddling about for years and also staring at Emily's diagrams, and she's got slightly different values here. She's used a 10 volt reference, which is useful because you can have less power wastage in this resistor. But 10 volt references are harder to come by than 5 volt ones. So I don't know. Anyway, so she's done that. But you can see a few different patterns here. So this one's quite cute. This one's got a knob on it, obviously, and it's being used to adjust the between the minus 10 volt reference and the 0 volt reference. And then she's relying on the fact that the STM has clamping diodes. And oh, actually, no, she's not just relying on this. I'll talk about that in a moment. Anyway, this is basically an offset knob. So basically, that's how you build an offset. You just change your reference. And there are different patterns. You could stick the pot across here, for example, and turn it into an attenuator. Just wire it up slightly differently. And if you want an attenuverter, you probably have to throw in an extra op-amp. But it's pretty easy. It's basically one op-amp and a knob will give you a ±1 scale factor on the knob. So that's an attenuverter. And again, the building blocks here are just the same across every single module. I know some people have actually built these little things as circuit boards that they then sort of wire together like Lego. And again, that's what I'm really stressing. This is just Lego blocks for grown-ups. And yeah, the nice thing about MCP6004 is it's a rail-to-rail op-amp. So basically, the trick that she's using, and everyone has copied, is basically you run it from 0 and 3.3 volts. So somewhere the power supply for this is here. Yes, here it is. And she's running it from 3.3 volts and ground, which basically means the output can't be outside of that range, so it's not going to blow up your processor. But the input, as long as it's biased and scaled carefully, can be, because the sum points are all within that range. So basically, the beautiful thing about using this chip is if, for example, you have a massive minus 12 volt swing, someone plugs in a massively hot jack plug, this lovely little chip will clamp it to its 0 to 3 volt range and not blow up your CPU. Whereas on the output side, oh yeah, and if you want to trigger inputs, even simply, you just use a transistor. Classic. And in fact, she uses a 10K pull-up, which isn't, I don't think that's necessary because you can drop that and just use the pull-up inside the chip and configure it to do pull-up. So I'm not quite sure why she's done that. I certainly don't bother, so I drop that resistor. Excuse me. I should be coughing into my elbow, but I shall wash my hands for 20 seconds. Stay safe, everybody. Don't do what I just did. This is the power supply regulation section. I'd be interested to know, actually, she always has a separate analog and digital regulators, which I've started copying because I had a bit of noise on some of my earlier designs when I didn't do this. Some people just do one and then stick an inductor between them. Oh, look, here's that regulator diagram that we just drew. We drew it way prettier than her. Look at that. Look at that. It's beautiful. Oh, ugly. Kidding. Yeah, so she has 2 regulators. One for, as I say, she goes all the way from 12 volts straight down to 3 volts 3. So basically you're boiling an ocean here, and then you're boiling another ocean over here. I tend to go for 5 volts off the 16-pin power. But yeah, separate regulators, I guess, for noise. But then she doesn't have separate ground lines. So some people recommend that you have your analog ground, your digital ground separated. But she doesn't. So I've copied that, but I don't actually have a deep understanding of why that's a good thing to do. But anyway. Yeah, LEDs, if you want to light up blinking lights, it's even easier. You just, follow every tutorial blinking light tutorial, but it's basically pin from digital thing, whether it's a chip or a CPU. Small resistor, 68 ohms, wow, that's pretty low actually, into a bicolor LED in this case, and then down to ground. Easy peasy, lemon squeezy. Okay, I'm going to accelerate a little bit. I'm waffling. Let's have a look at the chat. La 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 la. Where are you, chat? I don't even know how to compute anymore. Oh yes, it's in YouTube. Yeah, about the analog purism. Yeah, I mean, I'm doing this for fun, and I think purism is something that keyboard warriors some people get pleasure out of taking a strong view, and I respect that, fair enough. And they have a certain kind of aesthetic they're going for, and I actually respect that, and I think that's a useful constraint. I do think analog things and Buchla things and that sort of stuff can have a wonderful warm sound to it. But I enjoy programming, I enjoy electronics, and I enjoy I'm not an expert at analog design. I don't particularly enjoy the tinkering on a breadboard of playing with a single transistor to try and get that perfect I don't know, saturation curve or whatever you do when you're designing analog oscillators. My version of that, my secret sauce, ends up being in the software. Horses for courses. My point is there's incredible learning resources out there, and the schematics for the mutable instrument ones were a huge inspiration. And I can now just spit them out more or less without thinking. But also because this is A-level electronics 101, inverting op-amp, diode, chip. Hiccups again. I'm going to show one I made earlier. In fact, I made 2 days ago. So close this down. I'll show one more thing before I discard changes. The next step, sort of in kicad, is there's a really good DigiKey sponsored YouTube series where with Sean Heimel, I think he's called, where he goes through, teaches you kicad, and that's everything I know in kicad I watched from those 5 20-minute YouTube videos. So basically, you annotate everything, which gives everything numbers, and then you have to assign packages to them. So basically, you have to choose what resistor you want to. You said you want a resistor and you want it to be 33K, but you haven't said how big it is. So this, oh, it's on the wrong monitor. Hang on a second. It's show me a modal dialog box I can't click away from, so we have to hold on a second. What makes a ground different? Doesn't it all go to the same place? The point about electricity, as I understand it, and this is going to be the sort of hand-wavy explanation, is that in fact, I'm going to, aside on noise and stuff and grounds, is logically, especially if you're a digital person, you're thinking in terms of the fact that this is called gate and this is called gate means that they're now one and the same, and everything that's called ground is just ground, and it is now 0 volts and just is a fact. And that's a fine first order approximation. But the reality is everything has resistance, capacitance and stuff. And everyone who is connected to that ground is basically trying to pull it up. I think of it like a rubber sheet or a kind of wobbly mixed analogy, but like water sloshing around or something like that. And your power supply is desperately trying to keep the ground line down. It's trying to hold the tent, the clothesline, I don't know, hold it at a particular level. And it's trying to hold the 12 volt line exactly 12 feet above the 0 volt line, right? So like a stiff power supply is basically is Arnie hanging out on the input pins of your module, literally physically up there by the input pins, trying to hold these two wires a certain distance apart electrically. And then everyone who's consuming power is basically trying to pull those together. And the electrons are actually literally sloshing around. And the problem is that when you imagine that you have a board, in fact, I'm just going to switch to a picture. Oh, where's OBS gone? You need it. Overhead. Right. So I'm going to randomly pick a board. I'm just going to pick this one because it's small. Okay. Power comes in here, right? And to get to these analog chips down here, the current has to flow down some traces, and then they consume it, which basically is pulling on the clothesline, if you like, and then the electrons literally flow back up here. But in the meantime, this guy is also pulling on the clothes peg, and all the other components are pulling on the clothes peg, and these ones are doing ugly digital high frequency garbage. And so basically, physically, because this is in between here and there, these little puppies are going to feel the wobbles coming from this changing its power consumption. So basically, the physical layout and the return path, and basically when you're laying out a PCB, you want to think about current loops. So basically the current has to get from the input pin through the thing that does the work and back up through ground. So although ground is ground and all of the wires are called ground, literally the electrons will be flowing through they're the laziest possible path. So they'll be flowing through the shortest path they can to get back to the ground. And along the way, they'll be basically inducing a voltage, which you'll see as noise, and which other chips and sensitive things can pick up on. So basically, ground is not ground. It's a different value at every point in your circuit. And everyone who's doing work, expending energy, is basically causing locally ripples and fluctuations. And so when you have an analog ground and digital ground, it's actually just a kind of layout thing. Although they ultimately end up at 0 volts, you control where the ripples can flow. It's like you're designing channels and you're preventing the ripples from spewing from one place to another place. So, it's all about careful layout to stop the electrons of one chip from fucking with the electrons of another chip. Right. That was a very long answer. Did that help? All right. I'm going to... what time is it? I have no idea what time it is. The time sponsored by Now is something o'clock. Okay. I'm only planning to do about an hour, but I may go a bit over at this rate. But, all good. This didn't go at all how I planned. I've waffled way more than I was expecting, but it's a bit more beginnery than I expected either, but as well. But it's all cool. So what I was doing was I was saying that I will switch my OBS back to my desktop. Would be good. We've done this design. We've completed our logical design. Now we need to turn it into a physical design. And the first step of doing that is, oh God, this window, which is on the wrong viewport, which is why you can't see it. Basically, these are all the components that we've chosen, but we haven't chosen what they're physically going to be. So I tend to use surface mount components. So basically, this is a capacitor. So we just want to go to the capacitor section, surface mount device, not an electrolytic, 0603. That's a nice sort of hand solderable, but also cheap size. So basically, we can say, right, all of these puppies are going to be 0603. Audio jack, I believe there's one called Quing Pung, I think is the manufacturer. I call them Thonkicon jacks, but I happen to know that that one fits the Thonkicon, so there goes a top tip in this thing. Here are some resistors. These are going to be 603 for the sake of argument. So we go to resistor. Where are you, resistor? Resistor surface mount, no longer with Quing in the name. And they're going to be 0603. Jolly good. Now, this is going to be available as a 604, probably a SO package. I want to match the number of pins. I'll go for a TSOP package, which is a small surface mount package. And I just happen to know, and I'm about to talk about how I know this, they've already filled in the package for the SCM because it only comes in one package, and they've already filled in the package for the LM404. So thank you, kicad library authors. So now we've assigned our footprints. We can actually design our board, and it still blows my mind how easy this is. So basically, you load up the layout bit of kicad, and I fully intend to write my own PCB layout software because I cannot abide any of the Eagle, horrible, commercial and horrible, kicad free, open source and horrible, so therefore better, but still horrible. So we just sync across from our design, and here are all of the bits, and voila, those are the pieces. And actually 2/3 of the battle of laying out a board is where you put stuff. So basically you just move them around with the M button. There's our amazing processor, there's our input jack, there's our op-amp, and the little white lines are basically the connections between them. So you can move and rotate them into place. Move this one, I don't know, I haven't actually hooked everything up properly, so the circuit doesn't actually make sense at this point, but sort of vague vibe. Here's our Zener diode. Blah, that'll do. Let's say that was my amazing layout. And we decide that we're going to make this in eurorack, so we basically want something that's about 5 inches, so we'll set our grid to 0.1 of an inch. Mils is 1/1000 of an inch. So we'll draw our awesome eurorack outline. So let's say it's going to be that wide by, I won't measure it, but let's say that's 5 inches. It wasn't 5 inches, but close enough. Job done. And then we can look at that in 3D. It's going to open on the wrong window, so I shall just move it. here is our beautiful eurorack design. It hasn't got very much going on at the moment, but there it is. And actually, I find this 3D views is actually really useful for debugging, oh my God, I physically put two things on top of each other or something like that, which is sometimes not easy to see. Let's see if the chat's exploding. Enjoying this very much. It's making me very cool. You can still hear me, is mainly what I'm checking. I apologize if this is all a bit of a mess, but I should say that I'm not an expert at this. This is me sort of sharing that I've gone from reading a bunch of YouTube tutorials, soldering a bunch of stuff by hand, building a bunch of kits from Thonk, enjoying a few bleeps and bloops, and actually realizing that you can build this stuff so incredibly cheaply. And the payoff of this whole stream in about 10 minutes is basically that the JLC PCB assembly service has changed my life. It's insane. And I'm not getting any money from them, sponsorship or anything saying that. It's a wonderful, wonderful thing. And I need to talk about constraints. In fact, I'm going to do that right now. So there was a time which I advise you to skip, where basically I would go through this process. I did an Eagle at the time. I'd design a schematic, right? So I'd design my schematic and I'd figure it out. And I'd spend a lot of time choosing components. So one thing I skipped over is like, how did I know that this is an LM404? Well, that one's nicked off mutable. How do I know that's an MCP604? And worse, how do I know what package it is? Because let me just show you what it's like. I mean, it's amazing and wonderful. The DigiKey and Mouser and whatnot exist, and RS Electronics. Let's go to DigiKey, shall we? And we'll just search for MCP6004. So we think we've been super specific, but look, these are all the MCP6004s available in DigiKey, and they're all and these numbers matter. Like one of the first mistakes I made was I was ordering an expensive DAC chip, and I didn't notice that one of the letters at the end, if you notice, is MCP604 T-I/S TTR-ND. How do you know what those letters mean? They're different for every single bloody component. And the only way to find out is to go and read the datasheet in detail, where they will explain to you what those letters mean. And it's different for every single component. And seriously, FML. So I'm going to, I have a magical trick for how to avoid all this, but I'm just showing you the pain of actually product selection, sort of chip selection, is a complete and utter headfuck. Here are some top tips. Always tick in stock. That cuts it down massively. Okay. If you've got a choice, cut tape. We know it's surface mount. Right, we're down to 5. Cut tape just means they don't send it to you on a gigantic plastic reel as if you're going to load it into your robot assembly device. You are a human. Cut tape's fine. It's basically arrives on a piece of tape. Then the only choice we've got left is basically big surface mount or little surface mount, and that's basically taste, up to you. If you're going to use an assembly service, I recommend the little surface mount, and then I guess you could look at price as well, but they're all 48p. Some of these will be automotive grade, so it'll be like they can run over a wider temperature range. So this one down here can only go up to 85 degrees. At this point, I'm like, whatevs, I'll take the top one. But that's a nightmare, right? Because you have to do that for every single component. And I mean, literally every single component. Let's say that we wanted a 33K 0603 resistor. It sounds like I've pretty much narrowed that one down, right? So I've literally said I want a 33 kilo ohm 0603, that's a specific size, 6/1000ths of an inch by 3/1000ths of an inch resistor. And there are 1,731 results. And I loathe this, and no one really seems to talk about this in the tutorials. They're just like, and then pick a resistor. And I'm like, I don't know. This is horrendous. So this is actually part of the genius of JLC, right? So if I go to JLC and double check that OBS is still alive, seems to be, and that you aren't all screaming at me. Is the layout quite difficult to avoid reduced noise? Do these layout apps handle this? I'll just quickly show a bit of layout actually. Sorry, I'm random polling. So basically this, we haven't laid it out yet. We actually have to manually lay it out. So you basically say, right, I want to go from here, and it's saying I have to hook, my grid is massive. Let's go down to a nice fine grid. So it's saying I have to connect this guy to this guy, this guy has to come down to here. And you can see it's sort of helping me out, but it's not helping me out that much. And I can kind of click around. I can draw my beautiful path. Where does it need to go again? Oh, the yellow line says it has to go over here. Let's go over here. And basically, if I did this, the electrons would be very sad. There we go. So that's a very bad path. And that's literally a piece of copper. It's going to get printed onto the circuit board. And you have to do this for every single wire. But let's say we had to go from here and we wanted to get down to that number 2. And we could go around the back. But you can also put in something called a via, which is by pushing V. Go onto the top side, which is green, and via back down onto the bottom side. And let's go back to the top side, back down to the bottom side, and hook it up. Okay, so these are little drilled holes physically in the board with some copper on them. And basically, the electrical connection goes up through the board onto the top side, back down to the bottom side. And you want to minimize the number of these vias, right? Because they add impedance and capacitance and mess to your signal. And you want to make the signals as short as possible. So there's a sort of meditative thing where you basically have maybe 500 of these connections to make across your board. And you have to untangle them, and you only have 2 layers to do it in, or maybe you have 4, depending on your pricing. And there are auto routers, and I do use them because I'm lazy, but you shouldn't. Everyone tells you that you should do it by hand, but I will admit that I tend not to do it by hand. I tend to use an auto router called free routing. Okay, I need to show you something. So now you can see the traces have been drawn. And as I say, this 3D view is really useful to give you a preview of what it's actually going to look like. And it has a ray trace mode as well, which is kind of actually pretty close to what it ends up physically looking like. So you can kind of really get a sense of have you messed up the physical layout of your board. So although at first I thought it was a bit of a wank, it's actually incredibly useful. And you see those vias, right? I went there, and then this one I went onto the underside of the board. So if we flip the board over, keyboard shortcuts for the win, there's nothing on my underside of my board apart from, I don't know my keyboard shortcuts after all, those 2 little green bits. So that those green lines turn into copper on the bottom of the board. All right, so back to constraints. So if you go to All PCB, which is another Chinese manufacturer I recommend, very good. It's amazing. Basically, what you do is you take your design, and there are tutorials of how to do this online, and you drag and drop your things. You choose the size, the color, sort of, multiple choice, and then they tell you the price, and they send it to you in 5 days. It's like magic. So you literally go from doodling this to uploading a zip file, clicking buy, and 5 days later, a completely customized thing to your design arrives in your doorstep. But it's a blank board, right? It's a board that is not got any components on it. And they do offer assembly services. So All PCB offer assembly. The tricky thing is, and I've done the assembly, so Plinky Expensive Edition was done by All PCB brilliantly, and the service was incredible. But I'd consider this assembly service quite traditional in that there were humans involved. They actually took spreadsheets from me and manually went through and actually bought the components. And many of the components I actually bought from DigiKey. So they actually went to this website and they bought the components for me to their factory, shipped them to China, loaded them into their robots. And all of this was specified through spreadsheets and emails. And it was actually quite time consuming. And the price they charged me was 100 or so quid. I can't remember exactly. It's still incredibly cheap considering the amount of checking and labor, and they must have gone to markets to buy, haggle over prices and get some markup and everything. JLC, just since September last year, have been offering this completely bonkers assembly service, right? Where at first I didn't realize it was different. I completely ignored. I assumed it was the same. They're all the same because the PCB manufacturer for all of them is basically the same. But JLC assembly seems to be different. And what's amazing about it is its price. I'm just going to double check that. Yeah, so this is going to make part selection. This is going to solve the part selection problem and also be incredibly cheap and also mean that we don't have to do hand assembly for 4 hours at 2 in the morning. It's just changed my life. So How have they made it so cheap? And the answer is it's insanely limited. Okay, it's only a single side, only surface mounts. That means no knobs, no jacks, no connectors of any kind, no LEDs, nothing with holes. Hiccups again. Have some water. You can't have very many. I think that's a typo. Basically, bugger all copies. So you couldn't use this for actual manufacture. You can only do 2 and 4 layer. You can only do green. God knows why. You can only do certain thicknesses. You can only do up to a certain size. There are only 689 so-called basic components, and there are only 30,000 extended components. Now, at first I thought, this is a disaster. And the hilarious thing is, I think 30,000 is an overestimate. So let's follow their example and do the same thing I did on DigiKey and type in a 33K resistor 0603. And basically, already I can see there's one that's a basic part, 33K, job done. That's it. I'll get to what an extended part is in a minute, but basically, if you can get a basic part, get a basic part. And there are only 689 basic parts in total across all of electronics for JLC. And they will only assemble from this selection, right? So what they've done somehow, they've also cut out stencils. So basically, I think they're 3D printing the paste onto the board automatically, completely cutting out an entire manufacturing step. Awesome. Then they are clearly have some crazy warehouse robot system for getting a very limited set of parts over onto their robots. And then they can assemble for $7. So there can't be a great deal of and I'm going to show this process in a minute before that, because I've just got to show it. Even though the stream is now overrunning, I've got to show this because it blew my mind. So suddenly, my new rule for myself, and constraints are good, right? Is I will only design things that fit within the JLC 30,000 part envelope. And I should say that it doesn't matter if you design something that's outside that, because you can always hand solder it yourself. They'll assemble everything they can. So people are doing stuff where they do all of the passive components, these little resistors, using the JLC assembly, and then they have their fancy chip that JLC don't do, and you solder that on at home. But the thing that surprised me was, if you search for STM32, they have like 297 different flavors of STM processor. So it's incredibly well represented. And if I know that I want the F4 family, even within the F4 family, I've got 44 items. Now, note that their stock is quite often 0, which sucks. Now, in my most recent design, I was using an F405, and just because I know that that's a basic part. So the hilarious thing is they have 3 basic parts. They always have masses of stock. And I don't know if you noticed the price on that resistor, by the way. 33K 0603, $0.0016. And that's what they charge you for it. I mean, what? How does that even work? So yeah, STM32 F405. It's kind of vanilla STM processor. Loads of stock, $4, basic part. So what an extended part is, they have to go, probably a human is involved, basically. They have to go and actually move it from one bit of the warehouse to another bit and load it onto the robot. So they charge you $3 for each extended part you use. You can have as many as you want, sorry, so each unique extended part. So I could have 10 of these ones. They charge me a $3 surcharge for going and finding 10 of them from their warehouse. And you can only have up to 5 or 6, I think, extended parts per design. But that's fine. So basically, you design your board to not have too many things. So to accelerate to the end, I'm going to put this on YouTube after, so if any of you need to go to bed or whatever, I'm sure you've all tuned out now anyway. So let's throw away our silly design and go back to one that we made earlier. Let's go on changes. So here's one I ordered yesterday. I literally sent this off to JLC yesterday. And I designed it over the last week in my evenings, and check this out. So I'm actually going to take you through the schematic super fast to show you that this is what I was actually intending to do the stream on. The entire stream was going to be this. Lol. But I got distracted. Now, don't be overwhelmed. Same exact STM chip as before. I haven't gone over how I choose which pin is which, and there's a very cool thing STM have called Cube IDE. but it's actually awful. But it has a very cool feature, which is a way of selecting pins. But I'll cover that in a future stream. I went around these pins, and for example, I said to you, oh, you want to pull reset low or boot. So that's what the capacitor does. You want to pull boot low unless there's a panic. So there's a little solder jumper there. So if you want to wipe your chip, you bridge that. Capacitors I showed you. Crystal, I said whack a crystal across it. I've whacked a crystal across it. And then all of these labels are just basically the inputs and outputs. So this design was the one where I had that little 8x8 LED grid. So I have 8 negative pins and 8 positive pins. So I've got N8765 and for negative, and P, I hate anode and cathode, I always get them wrong, so I call them negative and positive. I've got an encoder, I've got some other pins. Basically, Dell touchpad fail. I do miss my Apple touchpad. So basically every other pin on here is just a label for some other part of the thing. Here's my 8x8 LED array. It's an 8x2 pin array. Current limiting resistors for the LEDs, 16 pins, job done. Op-amps for the output, same pattern we drew earlier. Op-amps for the input, same pattern we drew earlier. Exactly the same, copy paste. You look, there's the voltage reference, exactly what we drew earlier. Here's some power supply regulators, superstitiously one for analog and one for digital. Here's the eurorack connector for the actual power. Here's my 3 knobs that I want. Here's my encoder, job done. So I've literally Lego bricked each of these things, and there's nothing to it. Literally, it's plonking down a part, labeling its pins, and then hooking them to the processor. So I did not engage my brain at any point. What was happening here was I have an idea in my head. I had a picture in my head of what I wanted this device to look like. I knew it wanted an encoder. I wanted an 8x8 grid of LEDs, which is actually the silly seed of the idea. I wanted 3 knobs, and I chose 3 because that's what I could fit on the panel. I wanted 4, but constraints. And that was it. And then this little puppy over here is the sound card on a chip. And like most digital chips, you just feed it a bunch of capacitors and a bunch of signals, and it spits out the audio at the end. It's that simple. So there's a couple of nice ideas actually in here. I'm just going to throw these out there. On the input, it's nice to know whether or not the user's plugged in a jack or not. And with analog designs or carefully thought through designs, unlike this vomited onto the page design. I mean, I think this probably took 20 minutes to draw, and you can probably tell it took 20 minutes to draw because it's a mess. If you carefully think it through, you design what you want the normalized connection to be. So often when you watch like Div Kids videos or something, it'll be like, and when you don't plug the jack in, it's normal to here. And that's what this pin is about. What I've done is made it about software. So basically, I've got a pin called sense that's normally going to be ground that I feed in here, so that if you haven't got a jack plugged in, the processor has control over what's being fed into its own input. And what I'm going to do is every second or so, I'm going to waggle. If the input seems to be silent, I'll waggle the sense pin up and down and look at my own input to see whether or not it's waggling in time with my waggling. And if it isn't, then I know that the eurorack jack is plugged in and someone's actually trying to feed me a signal. But if it waggles in exact time with my sense pin, then I know that I've not got a jack plugged in, and I can detect basically whether the jack is in. So that's a cute hack. And then, thanks to LPZW modules, I do the same on the output. So basically, here's my stereo output, AC coupled because of these capacitors. And is the chat alive? Yes, okay, so I've got my sound card on a chip. It's got its line out left and right. I need to amplify them to eurorack level, so I just do. AC couple means take away the DC component by slamming it through a capacitor, electrolytic in this case. This is like a fairly hefty amplification ratio, inverting because that's easier. Slam it out to the output jack, but I wanted it to be mono. So I wanted it to be, so let me show you a module for a moment. Bugger, where's OBS gone? I need to get better at this. So let's imagine for a moment that this was my module and that these are the output pins, and I had a left and a right, but sometimes you don't want stereo in eurorack, sometimes you want mono. So I wanted to make it that if you plug only one jack in, then you basically get a mono mix, and only if you plug 2 jacks in do you get the separate stereo. So the way you do that in analog is you'd feed the unused normal pin back into your op-amp and basically use up another op-amp to sum out the output. But I'm a software guy and I didn't have another op-amp spare, so I did it a different way, which was inspired. LPZW modules gave me this idea, and I kicked myself because I'd done it on the input side, but I hadn't done it on the output side. So what I do is basically the output comes out here, my own output, my module's generating like my thumping techno is coming out here. And if you haven't got something plugged in, it will go through here, through this divider, which is actually pulling it high. I'll get to why in a moment. But basically it's dividing it down and then shoving its own output into a sense2 input pin, which is actually an ADC pin. And I'm slightly risking it here. I'm hoping that the clamping diodes inside the chip mean it won't blow up if I drive that negative, because I don't have any clamping here. I probably should put clamping diodes, but I looked at the data sheet and it said there were clamping diodes. I've put some whacking great resistors here. I'll let you know if this blows up when I build it. See, I'm still a noob. Probably the engineers on the stream are going, put some bloody diodes in. But no, I'm not going to do any diodes. I'm too lazy. So I've divided it down. It's about half hotness. The fun thing is if you then plug a jack in, right? So you want the stereo. So you've plugged a jack into the second input. This becomes disconnected and this sense2 becomes pulled high. So basically I'll detect a DC constant high voltage, 3.3 volts on here, which is impossible because it's an AC coupled, AC coupled and ground referenced input. So basically if I see sense2 swing high for a long time, like more than 1/10 of a second, I know that someone's plugged a jack in and I should do stereo. And if I see audio wibbling in on sense2, then I know that there's no jack there and I should do a mono mix and I can do it in software. So that's about the only cleverness in this entire circuit, which is otherwise copy pasta of everything. And so that means therefore that clever bit is the bit that's going to go wrong when I get back from the manufacturer. Okay, so I did the design, I did the assignment, so I did the horrifying and nightmarish, so I opened it on the wrong bloody page again. Come on puppy, here we go. So I went through and assigned packages for everything, but the fun part was I didn't look on DigiKey, I looked on JLC with their tiny stock, which is amazing because I basically had no choices. It's glorious. So having assigned everything, we come back in here and we draw a design, right? So it's exactly what I did before, but here's one I made earlier kind of vibe. And it's opened it on the wrong page. Couldn't make it up really, could you? Ta-da! Let's get rid of my ground planes. So here are those chips laid out. All the analog stuff is down here. So this is your op-amps and the resistors. There's your little sound card on the chip in the middle. There's your processor. This is your great big LED array. 0.8 of an inch. When I say great big, the entire width of this thing is 1 inch and it's 5 inches high. These are my 2 power supply regulators and power in, and then 3 knobs. So I started with my layout. Before I put anything down, I decided, right, I want a knob there, knob there, knob there. Let's look at it in 3D. And it opens it on the wrong page. I mean, seriously? Let me just pull that across. So this is the top side. We've got, is the stream still going? Who's still with me? Amazing. Some people are still watching. Thank you. I hope you've enjoyed it, you masochists. So I've got a knob here, a knob here, a knob here. I've got a 8x8 LED array. I've got an encoder here, and I've got 6 jacks. 2 of them are outputs, 4 of them are inputs. These 3 correspond to these 3 knobs. So basically, I made it down here. I'm trying it out. So basically, all the wires are at the bottom. They get out the way. The knob kind of changes the program or the sort of preset, if you like. This is an encoder, I mean. So you've got your ABC input, which corresponds to your ABC knob. Then you've got the actual audio input, because this is an effects unit. I haven't said what it is, but I'll do that on another stream. And then stereo output with the magic that if you only plug one in, you get mono. And if we look on the back, a very busy layout. I squeezed everything in. So there's my output op-amps. These are my input op-amps, the MCP 6004. These are all the resistors to just do the thing. Here are the big output caps that remove the DC component. If you have little ones, you'd have a tinny bass. If you have big fat ones, you get big bass. There you go. That's my level of understanding. Here's your sound card on a chip. Here's your CPU. All of these little capacitors are just decoupling capacitors to give it a little bit of local juice. Here's your crystal resonator, 16 megahertz or whatever. Here's your little programming pins. I'll cover that in another stream. Eurorack power, job done. And laying that out, I used an auto router for this one because I was feeling lazy and I wanted to get it done in like a couple of evenings. But if I show you, if I delete all the tracks, it's a hilarious rat's nest, right? So if we get rid of the tracks. Lol. So that's what you get when you bring your design in. You lay out all the bits, and it's basically like, connect everything to everything. And you get here, and you put some music on, and you start wiring, and you're like, right, you're going to come around here, and then you're going to go down here, and then you're going to go to here, and it's actually super relaxing. You can watch a movie. This one has to go up here, yada, 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 this one, and they all cross over, and it's actually, faintly nightmarish. And eventually, this is a 4-layer board. You end up with all your wires. And I laid out the analog section by hand, and I laid out some of the digital. So I laid out the neat bits. So basically, you can see that was hand laid out. These were all hand laid out. I chose my part placement. Basically, what you find you're doing, or what I find that I do, is you're iterating between where you put the components and where you put the tracks, and you kind of move back and forth between the two. And auto routers can't do that. All the auto routers I know of can only place tracks. They assume that your components are in a really good place. And so if I write my own software, I'm going to do something very different. I have ideas, but it's much more give and take between where you place components and where you place wires. So the cool thing is you do this, and then you basically say fabrication output position file. And I'm now just going to show you, to wrap up, I'm going to show you what happens when you upload to JLC PCB, because I think it's super cool. So let me just let me open up a folder. I was going to cover front panel design as well, but I just haven't covered that at all. But the stream is way too long, so I'm not going to bother. Okay, so basically all of these files here were spat out of when I click buttons in KiCad, and I'm not going to do it because it's boring and you can read tutorials how to do it. But they spit out these Gerber files, which are basically like vector images of like copper here, hole here, blah, blah, blah. But the extra part is they spit out a position file, which is basically, and it opens on the wrong page because God hates me. Right. Hang on. There it is. So again, it just spat out a file. Annoyingly, you have to rename the title. So hilariously, JLC say you have to call it designator val package mid-X mid-Y rotation layer, and KiCad calls it ref val package sen-X sen-Y rot and front or something. So you have to change the heading by hand, which is completely boring and manual. And all it's done is it spat out saying there is a 10 microfarad capacitor with this footprint at this position at this angle on the bottom layer, right? So that's just a list of all the things on our board. And then the other thing you can spit out automatically is a CSV called the bill of materials. Okay, so it's basically saying this 100 nanofarad capacitor, we have lots of them. There's like a bunch of capacitors all the same. And you want to, when you design for manufacture, you want to minimize the number of unique components. I haven't done a very good job here. I've got a bunch of different sizes of resistor capacitors, but it's also cheap at this point. I don't care. And basically what I've done is I've manually filled in the stock number for JLC. So basically this is their stock number for like each of these components. And I literally just went on their website. I've lost my website. I went on this website and you say, yes, I want that one. And it gives you a number, C15742. So you dutifully go over here and you fill it in. In fact, it might even be STM C15742. All right, people, the end is here. Let's get a quote for this exact board. I've actually already placed this order, but I'm just going to place it again, right? So I'm going to get a quote, and I go to my file of stuff, and I zip up all the files, and I drag and drop them here, and it uploads it. Internet, come on, you can do it. It shows it to me, and it proves that it understands the file. It says it's 107 by 25 millimeters, which it is. It's showing me the front and the back. It says 5 of them. Default options are fine. $32 because it's 4 layers. If this had been 2 layers, this would have been about $2. But because it's 4 layers, they charge me a more sane amount of money. But to be honest, 33 for 5. This is not for 1. This is for 5. So it's $6 each. So fine. Then the magical part. That's what you can get this on all PCB. You can get this from other suppliers. They're all the same. The part where GLC are magic is you say, right, assemble the bottom side because they only do 1. I only want 2. Jolly good. Hang on. You give it the and you tell it which side. What's going on? Assemble bottom side. Yes. Then I add the bill of materials file that I showed you. So that's like, oh, it's actually not there. It's there's that BOM file. There you go. Give it a bill of materials. It's just an Excel spreadsheet, and we'll give it the positioning, bottom positions. And we say next. This bit of the website's a bit buggy actually. About 1 time in 2, it doesn't work. So it reads the spreadsheet and it shows it back to me. It basically shows you all the prices, and the prices are all ridiculously cheap, apart from the CPU, but it's a CPU, so fair enough. And everything's in stock, everything's confirmed, and this is just ridiculously how easy this is. My brain was exploding at this point. So I say, yep, jolly good. Then it shows you a picture of what the robot is going to assemble. And a word of warning, kicad basically has every single chip at a random angle compared to what JLC expects. So I had to go and edit that spreadsheet, all the angles by 90 degrees or 180 degrees. All my chips were off. So the point of this display is to show me what the assembled board is going to look like. And I go and make sure that the plus as a component lines up with the plus that I labeled on the board, and that the pin 1 fits with the pin 1. And actually, this is where the 3D view in PCB is incredibly useful, right? Because you can bring up the PCB view and you can kind of A/B the red spot's there, the white spot's there. Okay, let's look at the chip. Red spot there, white spot there. Nobody else has this. As far as I know, JLC, well, certainly all PCB assembly doesn't do this. This is all done by hand with photographs and humans and lovely people. Like, I have nothing against the all PCB service, but it was much more manual. And look at the prices here. So we've basically got all in, including the PCBs and the manufacturing and all the components, for 5 PCBs and 2 fully assembled is $80. And if I'd clicked 5, I would have got more of a amortization of this. That wouldn't have gone up if I'd got 5 copies. The only number that would have gone up a little bit is that one. So probably, let's say it'd be $100 for 5. So it's $20 each, and I've just got a eurorack module for 5. I don't know, that blows my mind. And the thing that they send you back, just to remind you, is, oh, OBS, where are you? That, right? That's actually, that's the same size. It's a different design, but same PCB size. So for like the order of $100, I got 5 of these. It's insane, amazing. And it's just become a really pleasure. And then I manually solder on the physical heavy bits. I buy my jacks from thonk.co.uk. Shout out to Steve. So I bought the pots in there as well. I bought the encoder from RS in the UK, and the USB port. And you plug it in and you bring it up. So I'm actually going to do a stream about how you bring one of these modules up. And I'm planning to do that when the new boards arrive for the design that I just showed you, Wagyu. And I'll probably do the bring up live over a series of streams. And it may go horribly wrong, and those synths ideas may break, and you may see me crying on stream. But I think that actually makes it more interesting. So it'll be real. So when they arrive from China, I will disinfect them for 24 hours, but they will have been on a plane for 3 days at that point already. So um, at this point, I think I'm more likely to get infected by my prime minister than I am by any PCB employees. And we will see, or by myself, given that I've been coughing. But I don't have a fever. I'm going to go and wash my hands. Wash your hands. Everybody go and wash your hands. You've watched this stream. You've watched me cough. Now you have to go and wash your hands. So yes, as I say, honestly, JLC are not giving me any kickbacks for this. I just truly think it's amazing. And I think what's interesting about it is I wish it existed in Europe and America, and I feel like it could be competed with. And some people are just going to say, oh, slave labor, China. I don't know. I don't know whether that's true or not. But it seems very clear to me that they have innovated by adding loads of constraints. There's loads of clever constraints there. The board size is limited, the color is limited, the stock is super limited. The lack of a stencil implies to me that they have a completely different process for manufacturing that they're not talking about. So the way they make these boards is not the way that other people are making them. There's no stencil process. I think they've innovated their way to this service, and I think it's a game changer for me because it means that I can make fun little musical devices in small quantities for very reasonable amounts of money, like less than it would cost me to buy a commercial eurorack module, and I designed it. And the satisfaction of building something and having it arrive is just enormous. And then you get the fun of a little bit of hand assembly just to give you that sense of craft at the end. And I didn't end up covering the panel design, but basically I just drew a panel on PC in kicad without bothering to do any wires. And if you're very careful, you line it all up right. Hang on, get it right around. Which way around is it? It's that way around. Fits together, and looks quite professional, really. Stick some knobs on it. That's a D-type knob. I haven't got any nice knobs. Have I got any nice knobs? That will do. I don't know whether that's going to fit. This is a D-type knob. Right. Alex fails to put knob on. There we go. There you go. Look, it's a eurorack module. Shove a blue one on there. Love it. Perfect. So fun. So easy. No brain required. It's just patterns. Go and look at the open source schematics of other people. I will publish mine as soon as I get a module that's actually worth sharing. I think BVO is a candidate. I think Plinky is my favorite, although I'm going to iterate design until it's super perfect. I think Wagyu could be interesting. And I'll bring that one up on a series of streams, perhaps, in a week or two. Thank you very much for coming to my inaugural stream. I probably didn't click record on the audio, so probably it's been silent for an hour and a half. But, it was fun. I enjoyed it. I enjoyed talking into a screen for an hour. Stay safe, everybody. Look after yourselves, and see you next time. And now I have to find the stop button, which I have no idea where it is. Lol. Bye.